right, welcome to another deep dive. Today we're going to be exploring how modern Java applications are really put together.
Yeah, and particularly today, we're going to be focusing on two pretty important aspects of that, which are how these applications are structured and also how they deal with data, which is kind of crucial, right?
Absolutely. So, to guide our deep dive today, we're going to be drawing on a couple of sources. One of them is connected to this SWT Ubug Ausarbeitung, which is
Yeah.
essentially like this in-depth exploration of a project built using the SWT framework.
Right, right. So we can see how these concepts actually play out in a real project.
Yeah, exactly. And then alongside that, we'll be using some like fundamental explanations of Java annotations and this whole concept of OR mappers.
Which is a really crucial part of connecting your Java code to a database. And it's something that, if you're building applications, you're very likely to run into.
Yeah, you're going to need data at some point.
Yeah.
So the goal here, I think, is to really give our listeners kind of the essential insights into these tools and concepts.
Yes, and how they all fit together.
But without overwhelming anyone with tons of super technical jargon.
Right. We want to keep things practical and focused on how these concepts actually impact how you build applications.
Right. So let's jump right in. Let's start with Java modules.
Okay, sounds good.
Now, for those of us who've been around for a while, we might remember what it was like to build larger Java applications before Java 9 came along.
Yeah, things could get a bit messy, a bit difficult to manage sometimes.
Right. Yeah, it felt a bit like the Wild West sometimes. But with Java 9, we got this thing called the module system, and it really brought a much-needed sense of order to the way we structure and organize our Java code.
Exactly. It's all about bringing structure, managing dependencies, and actually it also enhances security by keeping different parts of your application nicely separated.
Right, because, before modules, we were mostly relying on packages to organize our code.
Right. Yeah, yeah. And packages are good for grouping related classes together, but they don't really give you true encapsulation. So in a really large application, any public class within a package could potentially be accessed from, anywhere else.
So it's kind of like everything is out in the open. There aren't really any strong boundaries.
Right. And the Java module system really changes that. The way it does that is by introducing this module-info.java file, which I'd say is kind of the cornerstone of the whole modularity system in Java.
Okay, so module-info.java. What is that and where do we find it?
So you'll find this file in the root directory of each module source code.
Okay, so every module has one of these.
Exactly. And it basically acts as a blueprint for that module. It clearly defines the module's identity and how it interacts with other modules in your application.
Yeah.
Inside this file, you use these specific directives, these keywords, to define exactly how the module fits into the bigger picture.
So it's kind of like the module's declaration of independence. Here's who I am and here's who I depend on.
Yeah, that's a good way to put it. So one of the most fundamental directives that you'll see in a module-info.java file is the module directive. And it's pretty straightforward. You just follow it with the unique name that you've chosen for your module. And that name acts as the module's identifier.
Okay, so it's kind of like the module's ID card.
Right. Then you have the requires directive. And this one is really key for managing dependencies between modules. So if your module needs to use code from another module, you have to declare that dependency explicitly using requires and then the name of the module that you need.
Right, so you're being very specific about what your module relies on.
Exactly. And what's great about this is that the module system actually verifies that all the required modules, not just the direct ones, but also any modules they depend on, which are called transitive dependencies, are actually present.
Oh, so it checks the whole chain of dependencies.
Yeah, both at compile time and at runtime. And this is like super helpful because it drastically reduces the chances of those really annoying class not found exception errors that you might get when you try to run your application.
Right, so no more surprises at runtime, like suddenly a library is missing?
Exactly. It makes your applications a lot more stable and predictable.
So we've got module to define the module itself and requires to specify its dependencies. What other important directives do we typically find in this module-info.java file?
Okay, so another vital directive is exports. And this is where you define which packages from within your module should be visible and accessible to other modules.
Okay, so you're specifically choosing what to expose to the outside world.
Exactly. And it's important to note that you export entire packages, not individual classes. And only the public types, classes, interfaces, and enums within those exported packages can actually be used by code in other modules.
So it's kind of like creating a controlled interface or API for your module. You're being very deliberate about what you allow others to access.
Right, right. And this is a key mechanism of how the module system enforces really strong encapsulation. Anything that's not explicitly exported is considered internal to the module, and it's effectively hidden from the outside.
Right. So it's kind of like creating those clear boundaries we were talking about, preventing accidental coupling between different parts of your application.
Exactly. It really promotes better code organization and maintainability in the long run.
Okay, so we've covered module, requires, and exports. Now, our outline also mentions a couple of other directives, provides and uses. These sound like they have something to do with services, right?
Yeah, you're right. So these directives are really central to how the module system supports this idea of a service-based architecture, which is a really powerful way to design more flexible and loosely coupled applications. The idea is that you have these well-defined services or contracts, usually interfaces, and then you have different implementations that can fulfill those contracts.
Okay, so it's kind of like defining a standard for something, and then you can have different providers that meet that standard.
Exactly. And the module system provides a really elegant way to manage this through these provides and uses directives. So the provides directive, the full form is provides interface with implementation. And you use this to register concrete implementations for a specific service interface. It's basically saying, hey, for this well-defined interface, I offer this specific class that fulfills its contract.
Okay, so it's like declaring, I provide this service, and the uses directive would be on the other side of that, right?
Right. The uses directive, and the full form is uses interface, declares that a module intends to use a particular service interface. It doesn't specify which implementation it will use, just that it needs one. And this is where a really cool mechanism called the service loader comes into play.
Ah, so the service loader kind of connects the dots at runtime.
Yeah, exactly. At runtime, the service loader can discover and load all the implementations that have been registered using provides and then match the interfaces that have been declared with uses.
Okay, that's a really clever mechanism. Can you maybe give us an example to help illustrate how all of this works in practice?
Sure. Let's take a look at the SWT Übergausarbeitung project you mentioned earlier. Specifically, let's focus on the Elm adapters and Elm client modules.
Right. So these modules are about interacting with these large language models, like, the AI systems that can generate text and code and stuff.
Exactly. And the way they're structured is a perfect illustration of these service-based design principles. So if you look at the module-info.java file for this swt.element.adapters module, you'll see that it includes this line. Exports swt6.modular.llm. That basically means that other modules can access the public classes within that package.
Okay, so it's exporting this package that presumably contains the adapter code.
Right. But then even more interestingly, you'll see this provides directive. Provides swt6.modular.llm.llm.llama adapter. swt6.modular.llm Gemini adapter. This tells us that the swt.lm.inline adapter. This tells us that the swt.lmm.adapters module offers two different implementations for the LMMI interface.
Okay, and those implementations are called Llama adapter and Gemini adapter. So presumably those are adapters for different language models.
Exactly. Now let's switch over and look at the module-info.java file for the swt.llm.client module. You'll see a line that says requires swt.llm.adapters, which makes perfect sense because the client module needs those adapter implementations to be able to talk to the language models.
Right, that's the dependency we were talking about earlier. It needs those adapters to function.
Yes. And then you'll also see this line. Uses swt6.modular.llm.llm interface. This tells the module system, hey, this client module needs an implementation of the LLM interface to work.
Okay, so the client module doesn't care which implementation it gets as long as it implements the LM interface. It's leaving that choice up to the service loader.
Exactly. So at runtime, when the LLM client starts up, it can use the service loader to find all the available implementations of LM-LM interface, which in this case would be the Llama adapter and Gemini adapter provided by the swt.llm.adapters module.
Okay, I see how it all comes together. It's really quite elegant how it promotes this loose coupling between the client and the adapters.
Yes, it is. And this leads to several really significant advantages when you're building larger applications. It makes your code much easier to maintain and extend over time. So for example, if you wanted to add support for another language model, let's say one called Superbrain, you would just need to create a new Superbrain adapter class in the swt.lm.adapters module, have it implement the LLM interface, and then register it using the provides directive in the module-info.java file. The client module wouldn't need to change at all.
That's amazing. You could add new functionality without having to touch the existing client code.
Exactly. And that's the power of modularity.
Right. So to just quickly recap the benefits of the Java module system that we've seen in this example, we get better encapsulation because things that are not explicitly exported from a module are hidden, which reduces the chances of accidental dependencies and makes your code more robust. We get explicit dependency management with requires, so we know exactly what each module depends on, and that helps prevent those runtime errors we were talking about.
And it helps a lot with versioning, too, because you can specify which version of a module you require, which can prevent conflicts if different parts of your application need different versions of the same library.
Right, that makes sense. And finally, we get this really modular approach to development where you can add or change things without having to modify a bunch of other code. And, if we compare this to the pre-Java 9 world where we mostly just used packages, it's like night and day.
Yeah, the module system really addresses a lot of the limitations of the old approach. Before Java 9, with just packages, any public class was potentially visible to any other part of your application.
Right, which could lead to all sorts of tangled dependencies.
Exactly. And it made it really hard to make changes safely because you never knew for sure what other parts of your code might be relying on something you changed. So the module system really brings order to all of that chaos. You have explicit control over visibility with exports. You clearly define what each module needs was requires, and you have this really well-defined mechanism for services with provides and uses, which promotes a much more decoupled design.
All right, I think we've covered Java modules pretty thoroughly. So let's shift gears a bit and talk about how Java applications interact with databases, which is another crucial aspect of building real-world applications.
Right. Most applications need to store and retrieve data at some point.
Exactly. So our outline mentions these things called OR mappers, and specifically JPA and Hibernate. Now, for someone who might not be familiar with these terms, can you explain what an OR mapper is?
Sure. So OR mapper stands for Object-Relational Mapper. And basically it acts as a bridge between the world of object-oriented programming, which is how we write Java code, and the world of relational databases, which is how data is typically stored.
Right, because in Java, we work with objects that have data and behavior. But in a database, everything is stored in tables with rows and columns.
Exactly. And an OR mapper, like Hibernate, helps you map your Java objects to tables in a database and vice versa. So you can work with your objects in your Java code, and the OR mapper takes care of all the details of actually saving those objects to the database and retrieving them from the database. It handles all the complex SQL queries and the mapping between your object model and your database schema.
So it's like a translator that speaks both Java and SQL.
That's a good analogy.
Yeah.
And in the Java world, there's this thing called the Java Persistence API, or JPA for short, which is a set of specifications that defines how OR mappers should work in Java.
Okay, so JPA is like the standard, the set of rules.
Right. And Hibernate is one of the most popular and widely used implementations of JPA. It's like a framework that knows how to follow the JPA rules and provides all the functionality you need to work with databases in a very object-oriented way.
Got it. So if you're using Hibernate, you're essentially using JPA under the hood.
Exactly. Now, when we talk about OR mappers, there are several key components to be aware of. One of the most important ones is the Entity Manager Factory.
Okay, Entity Manager Factory, what is that?
So the Entity Manager Factory is typically a relatively heavy object, meaning it takes some resources to create, and you usually create one per application or one per distinct persistence unit, which often maps to a specific database.
Okay, so it's kind of like the main connection point to the database.
Yeah, you can think of it that way. Its main job is to set up the connection to the database and to manage the creation of Entity Manager instances.
Ah, so that's where Entity Manager comes in.
Exactly. The Entity Manager is a much more lightweight, short-lived object, and you use it to actually perform operations on the database, like saving new objects, retrieving objects, updating existing ones, and deleting objects. Each unit of work you do with the database typically happens within the context of an active Entity Manager.
Got it. So the Entity Manager Factory sets up the connection, and then you use the Entity Manager to actually interact with the database.
Yeah, exactly. Now, another important component is the query interface. This interface allows you to perform queries on your entities, which are your Java objects that represent data in the database, using a special query language.
Ah, so you don't have to write raw SQL queries directly.
Right. JPA defines its own query language called JPQL, the Java Persistence Query Language, which has a syntax that's similar to SQL, but it operates on your entity model rather than directly on database tables. And Hibernate also has its own query language called HQL, which is very closely related to JPQL.
Okay, so you can use these query languages to retrieve data based on your objects.
Yes, and it makes it much easier to write complex queries because you're working with your familiar objects and their relationships rather than having to deal with low-level database details.
That makes sense. Now, our outline also mentions entity transaction. What's that about?
So entity transaction is all about managing the atomicity of database operations.
Atomic.
Yeah, so atomicity basically means that a series of database operations either all succeed together or they all fail together. You don't end up with half-finished operations that leave your database in an inconsistent state.
Right. That's crucial for data integrity.
Exactly. And you manage these transactions using the entity transaction interface. You typically obtain an entity transaction from your entity manager. You begin a transaction with tx.begin, then you perform all your operations, and then you either commit the transaction with tx.commit, which makes all the changes permanent, or you roll back the transaction with tx.rollback, which basically undoes all the changes.
So it's kind of like a safety net. If something goes wrong, you can just roll back and pretend nothing happened.
Exactly. Now, you mentioned earlier this execute and transaction pattern.
Mhm.
Have you come across that in your work with Java and databases?
Yeah, I think I've seen it used in some utility classes, like maybe a JPutil class or something like that.
Right, right. So execute and transaction is a really useful pattern for simplifying the whole process of managing the entity manager and entity transaction lifecycle. It's often implemented as a method that takes a piece of code as input, usually in the form of lambda expression, and it executes that code within a properly managed transaction.
So it kind of wraps your database code in a safe transaction block.
Exactly. And it handles all the boilerplate of creating the entity manager, starting the transaction, committing or rolling back, and closing the entity manager afterward. It really helps to avoid errors and ensures that your database operations are always executed in a consistent way.
Okay, so we've covered some of the main components of OR mappers. Now, how do these OR mappers actually know how to map our Java objects to tables in the database? That's where annotations come into play, right?
Yes, annotations are absolutely essential to how OR mappers like Hibernate and JPA work. You use these special annotations in your Java code to provide metadata about your classes and fields, and this metadata tells the OR mapper how to map those elements to the database.
So it's like adding extra information to your code that tells the OR mapper what to do.
Right, so one of the most basic annotations is @entity. You put this annotation on a Java class to indicate that instances of this class represent data that should be stored in a database table.
Okay, so if you have a class that represents, say, a customer or a product, you would put @entity on that class.
Exactly. And then you have the @id annotation, which you put on the field in your entity class, that represents the primary key of the corresponding table in the database.
Right. The primary key is that unique identifier for each row in the table.
Exactly. And then there's the @generated_value annotation, which you use together with @id to tell the database how to generate those primary key values.
So if you have an auto-incrementing primary key, you would use @generated_value to tell the database to handle that.
Right. And there are different generation strategies you can choose from depending on your database and your needs.
Okay, so we've got @entity to mark the class as an entity, @id to mark the primary key field, and @generated_value to specify how the primary key should be generated. What about the other fields in the class? How do they get mapped to columns in the database?
Well, for that, you use the @column annotation. You put this annotation on each field that you want to map to a column in the database table. And you can use this annotation to specify things like the name of the column, the data type, whether it could be null, and other constraints.
So you have a lot of control over how each field gets mapped.
Yes, you do. And then for relationships between entities, you have annotations like @manytoon, @onetomany, and @manytomany.
Right, because often your objects have relationships with each other, like a customer can have many orders, or an order belongs to one customer.
Exactly. And these annotations allow you to model those relationships in your Java code and have the OR mapper handle the foreign key constraints in the database.
Okay, so it handles all the database details for you. Now, the outline also mentions a couple of other annotations, @embedded and @transient. What are those used for?
So @embedded is used to mark a field as representing an embeddable object.
Embeddable object.
Yeah, so an embeddable object is basically a class that represents a composite value. It doesn't have its own independent existence in the database, but its fields are mapped directly as columns in the owning entities table.
Okay, so it's like a value object that's part of another entity.
Right. And then at transient is used to mark a field as not persistent, meaning its value should not be saved to the database or retrieved from the database.
So it's for data that's only relevant in memory, like a calculated value or something like that.
Exactly. Now, there's a distinction made between at embeddable and at entity, and it can sometimes be a little confusing. Can you maybe clarify that?
Yeah, that would be helpful.
So an at embeddable class defines a reusable component that doesn't have its own independent existence in the database. It's always used as part of an at entity.
So it's like a building block that you can use to compose other entities.
Yeah, you can think of it that way. And when you have a field in an at entity whose type is an at embeddable, the properties of that embeddable object are mapped as individual columns in the owning entities table.
Okay, so it's like the embeddable objects fields become part of the owning entities table.
Exactly. But an at entity, on the other hand, represents a standalone persistent object that has its own table in the database. And relationships between different at entity classes are defined using those relationship mapping annotations we talked about earlier, like at Manytoon and at One-Tomany.
So an at entity is a top-level object with its own table, and an at embeddable is kind of a nested object that's part of another entity.
That's a good way to summarize it.
Okay, that makes more sense. Now, let's talk a bit about these fetching strategies in LZY and eager that our outline mentions. Why are those important, and what's the difference between them?
So fetching strategies are all about how and when related entities are loaded from the database. And it can have a big impact on the performance of your application.
Right, because if you have an entity with relationships to other entities, you don't necessarily want to load all those related entities every time you load the main entity.
Exactly. So with LAZY loading, which is often the default, the related entities are only loaded when you actually access them. So if you have a customer entity and that customer has many orders, those orders won't be loaded from the database until you actually try to access the customer's orders.
Okay, so it delays loading the related entities until they're actually needed.
Right. And this can be a huge performance optimization, especially if you have large object graphs with many relationships. However, you have to be careful with LAZY loading because if you try to access a lazily loaded association after the entity manager that was used to fetch the main entity has been closed, you'll get a lazy initialization exception.
Ah, so that's something to watch out for.
Yeah, it's a common pitfall with LAZY loading. Now, with eager loading, on the other hand, the related entities are loaded immediately when you load the main entity.
So it's kind of like load everything all at once.
Right. And while this might seem simpler, it can actually lead to performance problems if you have a lot of relationships and you don't actually need all that data. So it's generally better to default to LAZY loading and only use eager loading in very specific cases where you know you'll always need the related data.
Got it. So LAZY is usually better for performance, but you have to be careful about the lazy initialization exception.
Exactly.
Now, the outline also mentions this mapped by attribute. What's that about?
So the map by attribute is used in bidirectional relationships where both entities in the relationship have a reference to each other. For example, if you have a customer entity and an order entity, and a customer can have many orders, and an order belongs to one customer, that's a bidirectional relationship.
Right, because you can navigate the relationship from both sides.
Exactly. And in these cases, you need to tell JPA which side of the relationship is the owning side and which side is the inverse side. The owning side is the side that actually manages the relationship in the database, usually through a foreign key column. And the inverse side uses the mapped by attribute to refer back to the owning side.
Okay, so it's basically a way to avoid having redundant information in the database.
Right. It prevents having two foreign key columns, one on each side of the relationship, which would be unnecessary and could lead to data inconsistencies.
That makes sense. Now, what about at Manytomany relationships? They're often used with set collections, right? Why is that?
Yes, that's right. So at Manytomany relationship is a relationship where many instances of one entity can be related to many instances of another entity. For example, a student can attend many courses, and a course can have many students.
Right. It's a many-to-many relationship.
Exactly. And in the database, these relationships are typically implemented using a separate join table that contains foreign keys referencing both entities in the relationship.
So it's like an intermediary table that connects the two main tables.
Right. And in your Java code, you typically represent these at Manytomany relationships using set collections.
Set. Why not list or something else?
Well, a set guarantees that you won't have any duplicate entries, which is important because in a many-to-many relationship, you don't want to have the same entity appearing multiple times in the collection. It should only appear once.
Right. That makes sense. So you use a set on both sides of the relationship to ensure that there are no duplicates.
Exactly. And you also need to specify which side of the relationship is the owning side and which side is the inverse side, just like with other bidirectional relationships.
Okay, I think we've covered up many-to-many relationships pretty well. Now, let's briefly touch on a couple of important entity manager operations. Persist and merge.
Okay.
So what's the main difference between these two operations?
So persist entity is the operation you use to make a new entity instance managed by the entity manager and subsequently saved to the database when the current transaction is committed.
Okay, so it's like saying, hey, this is a new object, save it to the database.
Right. But merge entity, on the other hand, is used to bring a detached entity back into the persistence context.
Detached entity, what does that mean?
A detached entity is an entity that was previously managed by an entity manager, but is no longer associated with an active entity manager.
Okay, so it's like an object that's been loaded from the database but is no longer connected to the entity manager that loaded it.
Exactly. So merge basically checks if an entity with the same identifier already exists in the database. If it does, it updates that existing entity with the state of the detached entity you're merging. And if it doesn't, it creates a new entity in the database.
So it's kind of like a save or update operation.
Yeah, you can think of it that way. And an important thing to remember about merge is that it returns the managed entity instance, which might not be the same instance you passed in.
Oh, so you should always use the returned instance after calling merge.
Yes, that's right.
Okay, now, the outline also mentions something about writing JPQL queries using entitymanager.createQuery. Can you tell us a bit about that?
Sure. So, as we mentioned earlier, JPQL is a powerful query language that you can use to retrieve data from your database based on your entity model, rather than having to write raw SQL queries.
Right, so you can query your objects using a more object-oriented syntax.
Exactly. And you use the entitymanager.createQuery method to create a query object that represents your JPQL query. You pass in the query string and the expected result type, which is usually your entity class or a collection of your entity class. And then you can set parameters in the query using methods like setParameter, and finally execute the query using methods like getResultList to retrieve a list of results or getSingleResult to retrieve a single result.
Okay, so it's a very flexible way to query your data based on your object model.
Yes, it is. Now, we've covered a lot of ground regarding OR mappers and how they make it easier to work with databases in Java. Let's shift gears once more and talk a bit about Java annotations in a more general context. We see them used extensively with OR mapping, but are they in a more general sense?
Yeah, they seem to be everywhere in modern Java code.
They are. So Java annotations, which were introduced in Java 5, are basically a form of metadata. Metadata is data about data. So in this case, annotations are data about your code. They allow you to add extra information to your source code, and this information can be used by the compiler, by tools, or even by your code at runtime.
So it's like adding extra information to your code that can be inspected and acted upon.
Exactly. And you can apply annotations to all sorts of program elements like packages, classes, methods, fields, parameters, and even local variables.
So it's a very versatile mechanism. Now, how do you actually define your own custom annotations?
So you define a new annotation type using the @interface keyword, followed by the name you want to give your annotation.
Okay, so it's kind of like defining a new interface.
Yeah, the syntax is similar.
Mm-hmm.
And within the annotation definition, you declare annotation elements, which look like methods, but without a body.
So they're like placeholders for data that the annotation can hold.
Right, and you can even provide default values for these elements.
Okay, that's convenient. Now, the outline mentions something about meta annotations. What are those?
So meta annotations are annotations that you apply to other annotations.
Annotations on annotations, so meta.
Yeah, it sounds a bit recursive, but it's actually quite simple. Meta annotations are used to provide information about other annotations, like their retention policy or their target.
Okay, so they're like annotations for annotations. What are some of the most important meta annotations?
Two of the most common ones are at retention and at target.
Hmm.
At retention specifies how long the annotation's information is kept.
So like whether it's only available in the source code or whether it's also available in the compiled class files or even at runtime?
Exactly. And at target specifies which program elements the annotation can be applied to, like classes, methods, fields, etc.
Okay, so it's a way to restrict where the annotation can be used. Now, what about the data types that annotation elements can hold?
So the allowed data types for annotation elements are intentionally limited to a specific set to ensure consistency and type safety. You can use primitive types like int, boolean, and string, enums, the class type, other annotation types, and arrays of any of these types.
So you can't use arbitrary objects as annotation
No,
values.
you can't. It's all about keeping things simple and predictable.
Right, that makes sense. Now, can you give us a concrete example of how you might define a custom annotation and then use it?
Sure. Let's say you want to create an annotation called @ReviewStatus to track the review status of different parts of your code. You can define it like this.